Hello everyone and welcome to CONVERGE tutorial series. I am Kislesh Srivastav. I'm a principal research engineer at Convergent Science, and today we're going to discuss a battery thermal management problem within CONVERGE involving a simulation of a pouch cell battery pack warm-up. So let's get started. So the case that we're going to discuss today can be found in our official studio example cases. We go to File, Load Example Case. Electromobility, Pouch Battery Pack Equivalent Circuit, CHT Transient Laminar. This particular case setup includes a 4-cell pack of NMC pouch cells. Between a pair of pouch cells, you have your liquid cooling fins, and within the liquid cooling fins, you have an active liquid coolant being pumped through it. This is a liquid-solid CHT simulation that we're going to perform. We have some acceleration approaches to speed up the simulation because we're going to run these simulations in the order of 40 minutes of physical time. We have these different parts in the geometry in their own separate regions and boundaries, as you can see here. We have sources, energy sources enabled in the simulation to heat up the battery, anisotropic conductivity for the battery thermal properties, and a grid control strategy. Now we're going to start setting up the case from scratch. We're going to start with our CAD file. The CAD file can be imported by going to File, Import, Import CAD file. We have a step file for our pouch pack assembly. CONVERGE Studio supports the import of a wide variety of CAD formats, which you can find here. We're going to give a medium resolution for the triangulation of the CAD geometry. This is a CHT simulation, so we do require interfaces between different solid parts and also the interface between solid and fluid. In order to automatically create those interfaces during the import operation, we will select the non-regularized unite option. As you can see, when CONVERGE Studio identifies two mating surfaces, it will convert the common surface as a single surface that can be set as an interface for our simulation. Now, when setting up simulations of complex battery pack geometries, it is highly recommended that users start with a good CAD. A good CAD will allow you to easily move to the case setup part of your pre-processing without having to do too much geometry manipulation operations and cleanup. So within our import tool, when you import a CAD geometry and if the CAD geometry is well constructed and clean, you have the option to direct CONVERGE Studio to automatically assign interface boundaries and regions after the import operation. When you hit import, as you can see, CONVERGE has imported a clean, flagged pack assembly geometry. Not only that, but different parts of the geometry based on the CAD file have been flagged into different boundary IDs. They've automatically been assigned as a wall boundary for the outer surface, and Studio has automatically assigned an interface boundary ID for those different solid-solid interfaces, solid-fluid interfaces. Not only that, CONVERGE Studio has automatically created different regions for those different solid assembly parts. So with this approach, with a well-established or well-cleaned CAD geometry, you can easily move forward to setting up your case setup. In this tutorial, however, we are going to start off with an unflagged geometry, flag each of those boundary surfaces, and ensure that our geometry is clean and well constructed before setting up a case. So I'll repeat the import option without the automatic boundary and region assignment. File, import CAD file, turn these off, import the same geometry. We still want the non-regularized unite option that will create automatically the interface between different parts. Hit the import option again. All right. And we can go ahead and start to flag our different boundaries into the correct boundary ID. To begin with, I will select all triangles using the box selection option, and I will assign them to the not assigned group. Now I want to assign or create boundary IDs for my pouch cells, the outer surfaces of my pouch cells. And the different parts or the different surfaces in this geometry can easily be selected by the manifold option for triangle selection. Since the interfaces have been automatically created, an easy selection with non-manifold option is possible. I need 4 outer surfaces for my 4 cells. So I'll add 4 boundaries. I have 1 empty boundary ID. I'll create 3 more. I will rename them accordingly as cell 1, cell 2, cell 3, and cell 4. Now with the manifold selection, I will click my first cell surface, assign it to cell 1, second cell surface to cell 2, third cell surface to cell 3, and the final cell surface to cell 4. Now we will create boundary IDs for our current collector tabs. We have the positive tabs and the negative tabs. So I'll create 2 new boundary IDs. This I'll name it as tab positive, and this I'll name it as tab negative. So in this pack, we have 2 batteries connected in parallel and 2 pairs of 2 batteries connected in serial through a busbar connection. So our positive tabs we identify as these 2 tabs for cell 1 and cell 2. These 2 tabs on the opposite end will be our negative tabs for those cells. So this is our parallel connection. And then for a serial connection, the negative tabs connect to the positive tabs for the adjacent pair. I'll go back to positive, and then these 2 act as the negative tab for those pairs. Next, we construct a new boundary ID for our bus bar. We identify our bus bar connections and assign it to the correct boundary ID accordingly. We also have aluminum cooling fins. So we create a new boundary ID, call it a cooling fin. And through manifold selection, we assigned that to that particular boundary ID. We have coolant channels running through. We have an inlet coolant channel and an outlet coolant channel. So I'll create new boundary IDs. Let's call it coolant pipe in and coolant pipe out. This will be my inlet pipe, and on the opposite end, this will be my outlet pipe. I also want to enable flow for the coolant system, so I need to create inflow and outflow boundary IDs for the coolant pipes. So I'll do that as well. Create 2 boundary IDs that I call coolant inlet and coolant outlet. I'll select those inlet and outlet faces through angle selection. I'll select this face as my inlet. It goes through the coolant fins across coolant channels within the coolant fins, and then comes out through the coolant outlet. All right. So we have flagged all the outer surfaces. And now we want to flag interface boundaries for the inner surfaces. So you can clearly see if I enable the clipping plane, if I cut the clipping plane, you will see that there are interface contact surfaces between the cell and the coolant fins, between two cells which are in direct contact with each other, and also between the coolant fins and the coolant pipes and the cells and the tabs and the busbar and so forth. So let's first start with the interfaces that involve our four cells. So each cell is in contact with the coolant fin. So I will construct four interface boundaries. Let's call it interface coolant fin and cell 1. Interface coolant fin and cell 2, cell 3, and cell 4. Okay. The brown is my cell 1. So I'll go ahead and select that surface by manifold again. Front surface is for cell 1. The surface behind is for cell 2. Again, front surface is for cell 3. And the behind surface is for cell 4. We also have another contact surface between cell 2 and cell 3. They are directly in contact with each other, so I need to create a new interface boundary, and I'll term it as interface cell 2 and cell 3. And I'll assign that particular surface to that particular boundary ID. Right. Remove the cut plane here. And now we also have interfaces between the cells and the tabs, which are of different materials. So we have two interfaces for each cell. We have an interface between the cell and the positive terminal, and the cell and the negative terminal. As such, we will create 8 new boundaries. We will have interface between the positive tab and cell 1, cell 2, cell 3, cell 4. Similarly, we have interface between the negative terminal and cell 1, cell 2, cell 3, and cell 4. Right, let's go ahead and start with our positive terminals. I'm going to hide the positive terminals real quick so I can identify the interfaces. This is for cell 1, cell 2, cell 3, and cell 4. Now move ahead with the negative terminals. Cell 1, 2, cell 3, and cell 4. Okay. Finally, we have interfaces between the tabs and the bus bars. So I'll hide the bus bars real quick. I'll create a new interface. Create 2 new boundaries. And this one is the interface between the bus bar and the positive tab. This one is the interface between the bus bar and the negative tab. So I'll assign it accordingly. These are my positive tabs here. These are my nectar tabs. Okay. We also find an interface has been created within the bus bar material. In the CAD geometry, we had a single part for the bus bar connecting adjacent terminals or adjacent tabs for the parallel connection, and we also had another bus bar connector for the series connection. If you do expect contact resistance, either a thermal contact resistance or an electrical contact resistance for the on these surfaces, then you can go ahead and enable an interface within the busbar material. However, we do not expect or do not have any contact resistance between the different busbar connectors. So I will just go ahead and delete those triangles. Repair, delete, select those triangles and hit delete. And now we have a continuous busbar material that we can go ahead with. All right. Let's see what boundary IDs have not been flagged yet. Go ahead and hide our boundaries, and then we'll look at the not assigned boundary ID. All of the fluid associated bound interfaces have still not been flagged to the correct boundary ID. So we have a couple of interfaces here. We have the fluid interfaces for the inlet coolant pipe, the outlet coolant pipe, and the inner coolant channels. So I'll go ahead back to boundary flagging, create 3 new boundaries. We have the interface between the inlet pipe and the cooling fin. We have the interface between the outlet pipe and cooling fin. And then we have the interface between the tubes and the cooling fin. Right. So we'll select the inlet boundaries interfaces first by manifold, which are these. On the opposite end, we have the outlet interfaces with our outlet pipe, which are these. And then all that's remaining is these coolant tubes that are running within the coolant fins, and allowing you to cool the battery uniformly. So I'll select those boundaries, which are fluid solid interfaces for the tubes, and assign them to the correct boundary ID. Right. All that's remaining in the not assigned boundary groups are these faces that have been created due to the nature of our CAD file. We do not expect anything to block the flow across the coolant pipes and the coolant channels. So what we're going to do is we're just going to delete all of those remaining boundaries at that inlet faces. I'll just go ahead and select them by boundary, and I will go to repair, delete, apply. Right. Now all of our surfaces have been flagged to an appropriate boundary ID. Before we proceed with setting up a case, we do need to make sure that the normals are correctly oriented, especially for the CHT simulation involving many interfaces where the direction of the normal is really important to consider for forward and reverse regions. We'll start off by having a look at the normals for the outer boundaries. Looks like all those boundaries for the outer surfaces are pointing out of the domain, which is wrong. We want the normals to point into the domain. So I'll just go to transform, normal, reverse selection, and I'll select all of those triangles and hit apply. And now you see for those outer surfaces, all of those normals are now pointing into the domain, which is good. We will now focus our attention on the interfaces, which can be a bit more complicated. There is no in and out sort of domain for interfaces. There's a forward domain and a reverse domain. So I'll go ahead and hide the outer boundaries real quick. All right. So the first interface we have is the interface between the batteries and the coolant fins. Now, when I name the boundaries, I make sure that uh, the first ID here, or the first name here, is the forward side, and the second name here is the reverse side. So the forward side has to be the coolant fins. So the normal should be pointing into the coolant fins. If I look at the normals here, I see that they are pointing into the cell, not into the coolant fin. So I'll go ahead and reverse selection for that particular boundary. If I look at the opposite side, these triangles are correctly pointing into the coolant fins. So that's good. Interface CF and cell 2 is all fine. For cell 3, it is pointing into cell 3, so I'll go ahead and reverse that selection. And for cell 4, it is pointing in the coolant fin, so that's good. Since I'm done with those boundaries, I'll hide all those boundaries. We have the interface between cell 2 and cell 3. Let me hide all boundaries. Let me show cell 2 and cell 2 on this end. So based on my naming, the forward region must be cell 2, which is not currently the case. It is pointing towards cell 3. So I'll go ahead and reverse the selection there as well. All right. The other interfaces, the interfaces for the positive terminals and the negative terminals and the cell. So based on my naming here, all of the normals must point into the tabs or the terminals. Some of these boundaries are not pointing into the tabs, so I'll just go ahead and reverse selection for those particular boundaries, and now I'm good to go. Next, the bus bars and the terminals. Looks like some of those boundaries are not pointing correctly. If I visualize the bus bar, they all must be pointing up towards the bus bar. So I'll go ahead and select all the triangles. Let's do it by manifold in this case. These triangles, these ones, this one here. Now all triangles are pointing into the bus bar, which should be my forward region. Next, looking at the fluid side boundaries. It is a good practice to have the normals point into the fluid domain for fluid-solid interfaces. Looks like that's the case for the first set of coolant tubes, but for the second set of coolant tubes, it is not pointing into the fluid domain, it's pointing into the coolant fin solid domain. So I'll go ahead and change the normals here. Another option for changing normals correctly is using the propagate change option. I will select one triangle which is pointing in the wrong direction. I will hit apply, and it propagates that change and makes the normals consistent between all surfaces associated with that triangle. Now if I look at all my coolant tubes, they are pointing in the correct direction. I can look at these interfaces are also pointing into the coolant domain, so I'm good to go. And on the outlet end, those triangles are also pointing into the fluid domain, right? So appropriately orienting your normals for these interfaces is essential. And appropriate naming of these different interface boundaries can guide you in orienting your normals and setting up your forward and reverse regions when you set up your boundaries. Let's hit a redisplay. Let's hide the normals. Let's make sure that there are no intersections and open edges, as you can clearly see. Currently, Studio is reporting non-manifold problems. As soon as we assign these different boundaries as interfaces, these non-manifold problems will go away. Right. Now that we have a good geometry, we can go ahead and set up our case. So I'll go to case setup. I'll start off with setting up my streams. So stream 0 can be my fluid coolant stream. I will create a coolant region. Let's name it as R coolant. And next, I'll create a stream for my batteries. So I have 4 batteries, so I'll create 4 regions. Region cell 1, cell 2, 3, and 4. Now make this stream as a solid stream, as you can see here. Okay. Now I could very well, the fluids and the solids must be in their own streams. They cannot be in the same stream ID. You could group all of these solids, including the cells, the tabs or the terminals, and the coolant fins into one stream ID. But just for better organization of outputs, I have chosen to create new streams for different parts. So for different groups of parts. So for the cells, I have a stream 1. I have stream 2 for the electrical connections. So we have the positive tab, we have the negative tab, and we have the bus bar. And a final stream for my coolant fin. All right, and these 2 streams are solid streams as well. I also want to split up the fluid stream into different regions. So I want to have separate regions for my main coolant channels as shown here, and then I want a separate region for these inner coolant tubes. That will allow me to study region-based outputs, that will allow me to implement region-based grid settings and so forth. Go back to our stream settings, and in stream 0, which is our fluid stream, we'll create 2 new regions, which is a region for coolant in pipe and region for coolant out pipe. And the first region, I'll rename it as region for coolant tube. Okay. Go ahead, hit validate, click OK, and now we can begin with our case setup. Now this particular case is a time-based simulation. It's going to be a transient simulation looking at warm-up behavior for the particular battery pack. This simulation is a liquid-solid CHD simulation. So we're going to turn off gas, enable liquid simulation, also enable solid simulation. There's no chemistry involved, so we don't need to involve any reaction mechanism. We will, however, create a composite species for the coolant mixture that we're going to create. So we're going to enable composite species now. We have appropriate run parameters, solver settings enabled, boundary conditions, initial conditions. Since I created multiple fluid regions, I'm going to turn on events. Under physical modeling, this particular case for liquid coolant is a low Reynolds number flow. We do not need to model any turbulence. It's going to be a laminar case, so we're going to turn off turbulence. We're going to enable sources to enable heat generation within the different solid parts, including the batteries. And we're also going to enable anisotropic conductivity for appropriate directional-based thermal conductivity for the batteries to implement realistic thermal properties for that particular battery. Grid control, we're going to have some fixed embedding for refinement, and then we can go ahead and hit apply, click confirm, hit done, click confirm. All right. Start off with our liquid simulation. CONVERGE Studio offers a set of predefined liquids. You can try to find your coolant liquid in this database. If you do not find it in this database, you can always create a new coolant and input appropriate coolant properties, or you can go to our liquid calculator and get sort of the liquid properties and calculate them through these correlations that have been listed here, as you can see, and actually generate a new liquid.dat. For my case, I need water, which I'll pick this. And my coolant is also a mixture of ethylene glycol, so C2H6O2. All right. I have temperature-based liquid properties included in my database. I'll go ahead and hit validate, click OK. For solid simulation, I need those different solid parts. So I have aluminum cooling fins, I have copper bus bars, etc. So again, we have predefined solids. I can take aluminum, I can take copper. If you have some nickel strips, you can also include a nickel solid, etc. And then as you can see here, you have temperature-based thermal properties for the solids. My cell is an NMC, nickel, manganese, cobalt, oxide battery. I do not have thermal properties for that particular battery, so I'll have to, in the database, I'll have to create a new solid. I'll term that as cell NMC. I'll give an appropriate melting point for that particular battery. And my battery is going to have constant properties. The density is going to be 2380. The specific heat that I measured is going to be 1090. The thermal conductivity, for now, I'll just go with the in-plane thermal conductivity. It's going to be 30. And I'll show you how we can change that to anisotropic thermal behavior. And we're not going to do an electrical simulation, so we don't have to worry about electrical conductivity. Since the melting point is 1700, we require 171 rows. But since the properties are constant, I'm just going to hit the constant solid properties option, and the database will be automatically filled in. Going to hit validate, hit OK. Now, for the liquid simulation, for the liquid, my coolant is going to be 50% water and 50% ethylene glycol. And this composition is not going to change during the simulation. So I can set a single composite species with the fixed composition of those two individual liquid species. So I'll call this composite as ethylene glycol water, select this as a liquid composite, select the base species as ethylene glycol and water, and give an appropriate mass fraction of 0.5. Right. So as you can see, I've created a composite.in. Now I'll go to species, liquid species. I'll enable that composite as my liquid species, and for solids, I'll enable the aluminum, the copper for the bus bars. I don't need nickel for this particular simulation, so I'll just go ahead and select my cell material, hit validate, and then we're good to go with the materials panel. Under the run parameters section, this is a transient simulation. It's a time-based simulation, solving for CFD. The liquid flow is incompressible. It's low Mach number, low velocity. There's no pressure effects to consider. Under the miscellaneous panel, we're solving for momentum, we're solving for energy. It's just a single species, so we don't have to solve for any species as such. Right. Make sure my screen print is verbose, so make sure I can properly evaluate the simulation during runtime and assess its performance. Click OK. Under simulation time parameters, start time is 0. So I want to assess the warm-up behavior of the battery for 40 minutes. So that's going to be around 2,400 seconds. Transient simulation. So we are simulating a big duration of physical time here. You can give an appropriate selection for initial time step. We're going to use a variable time step algorithm for an efficient simulation. We're going to give it a minimum time step just to give it flexibility to recover. We do need large time steps, so I'm going to select a maximum time step of, let's say, 0.02 seconds. Given that we're going to run the simulation for over 2000 seconds, I do want this case to run fairly quickly. So I'm going to run these cases with high CFL limits. So I can take larger time steps and get quicker results. So I'm going to make a selection of large CFL limits for this particular case. And only the convection and conduction and diffusion CFL limits matter for this particular case. You're always free to also set recommended values or go to a similar example case in our database and grab those settings from there. Click OK. Now, given that I'm trying to run this case for 40 minutes of physical duration, I can make use of some of the simulation acceleration approaches that we have. One of the approaches that we have is fixed flow. With the fixed flow approach, we assume that for a particular duration, the fluid is quasi-steady. So we can freeze the fluid solution, and then we can solve for just the solid and periodically update the fluid solution at specified intervals of time. That sort of makes the simulation more efficient. We're not solving for the fluid fluid solution every time step. The fluid can quickly react to changes in solid temperature, so we can just periodically update the fluid solution for this particular case. I'll enable fixed flow. It requires a fixedflow.in. I'll enable it for stream 0, which is my fluid stream. There are no parcels here. I'll start from 0. I'll have fixed flow active for all of the simulation. This is going to be activated cyclically or periodically, and then I'll give a suitable cyclic period to make sure that the quasi-steady assumption for the fluid holds good. I've selected that as 60 seconds. So within a 60-second interval, I'm going to solve for the fluid for the first 2 seconds, and then after 2 seconds, I'm going to activate fixed flow till the end of the 60-second cycle, right? And then at 60 seconds, it's going to solve for fluid again. The fluid can quickly update its solution, and then at 62 seconds, it'll again freeze the flow and so forth. And by only solving for the solid at large time steps, you can really improve the performance of your case. Next, for this particular problem, I can give you some recommendations for solver settings. So this is an incompressible simulation, so I'll select the pressure-based solver. For incompressible simulation, I'll select a slightly higher tall scale or piezo convergence criterion multiplier. Since I'm taking a large time steps for this case, I'll give more maximum number of piezo iterations. And then looking at the high fidelity simulations, I'm going to go second order flux bending. I do also want the case to be fairly stable at large time steps, so I'm going to enable upwind on all directions. Right, nothing to be done in the miscellaneous panel. In the equations, again, since I'm running this case at larger time steps, I'm going to give it more flexibility and increase the number of max iterations for momentum, for pressure. For incompressible liquids, I'm not going to solve for such tight pressure tolerances. I'm going to loosen it a little bit to E6. I'm going to increase the maximum number of density iterations. Same with energy iterations. Now we have seen, especially for anisotropic solids, a selection of converge bi-city stab and the ILU preconditioner gives great performance with large time steps. So I'm going to make that selection for just the energy solver. We're not solving for species, but just as a good practice, I'm going to give similar settings for density, energy, and species as they're tightly coupled. Click OK. And then we're good to go, and then we can go ahead and move to boundary conditions. So for the boundary conditions, the outer surfaces are well insulated, so they're going to have a wall boundary condition with zero heat flux. And I'm going to assign this into the correct region, which is going to be region cell 1. I'm going to do that for all of these outer boundaries here. I can do them one by one, or I can just hit the copy option. I can copy to existing boundaries, select those remaining outer boundaries as shown here. Click OK. All right. And all I have to do is just update the regions. Cell 2, cell 3, as you can see, it's still adiabatic. Cell 4. This is your inlet pipe. This is your outlet pipe. Right. The coolant inlet boundary is an inflow boundary for my fluid. I am going to give a mass flow rate boundary condition. So for this particular case, we have 5 grams per second of coolant flowing through the coolant pipes coming in at room temperature, and the species is the ethylene glycol water composite that we have created, right? And this is going to be part of the inlet fluid region. For the outlet, we're going to have an outflow boundary with a pressure boundary condition of atmospheric 1 bar pressure. Right, I'm going to give 0 Norman Neumann as backflow boundary condition and assign the appropriate region ID, which is the coolant outlet. Now for the interfaces. So we're going to set boundary conditions for a number of solid-solid interfaces. So solid-solid interfaces between the aluminum coolant fins and your NMC pouch cells. So I'm going to select the interface boundary ID or boundary type. The forward region, based on my normal selection and my naming, is going to be the coolant fin. The reverse region is going to be cell 1. Right? It's a solid, so I'm going to use Dirichlet temperature boundary condition. And it's a coupled CHT interface, so I'm going to turn on the coupled flag. That's about it. And all these other solid-solid interfaces interface boundaries will have the same boundary conditions and boundary types, except for the region definition. So again, I can go ahead and hit copy from existing boundaries, and then copy to all of these different solid-solid interfaces that you see here. Okay, and all that's left is just to change the region IDs. So this is cell 2, cell 3, cell 4, and this is between, reverse side is going to be cell 3 because of my naming and my normal assignment, and forward side is going to be cell 2. This is your positive tab and cell 1. Positive tab, cell 2, positive tab, cell 3, cell 4. The same for the negative tab interfaces as well. Right, and then we have the interface between the bus bars and the positive tabs. And so forth. Right, so just double check that all of your interfaces and the regions, forward reverse regions, is set correctly. And then we're good to go. And now we'll deal with some of our fluid solid interfaces. So again, these will still be interface boundaries. The forward side in this case will be the inlet coolant tube. Reverse side is going to be my coolant fin, solid. Still going to be Dirichlet. There's no law of the wall because it's not a turbulent simulation. It's a laminar simulation. It's still going to be covered. All right. And then I can go ahead and hit copy, copy to existing boundaries, and select those remaining two boundaries. Okay. And update the forward side for the fluid. Lastly, I have my coolant tubes. Okay. And now our boundaries have been appropriately set with the correct interface boundary ID. Go to diagnosis, go ahead find. Now, as you can clearly see, the non-manifold problems have gone away because we have correctly defined our solid-solid and solid fluid interfaces. One final thing for this particular problem. Between these two cells, cell 2 and cell 3, there was actually a thermal insulation material. That we did not include that in the geometry since it was very thin and it's not really necessary to model a thin thermal insulating material. But we can mimic the effect of an insulating material between two cells by adding it as a contact resistance. So if I go to that particular interface between cell 2 and cell 3, you can set an appropriate contact resistance value based on the insulating material's conductivity and thickness. And I've evaluated that particular contact resistance value to be 5e minus 4. Next, we'll go and set up our initial conditions for our different regions. So for the coolant tube, I have my ethylene glycol water, right? And I'm going to give sort of a rough estimation of what the pressure is going to be. This is just the better the initial conditions, the more quickly you arrive at some sort of a quasi-steady result. For the cell, it's just going to be your cell NMC. The entire domain is going to start with ambient ambient temperature of 300 Kelvin. You're looking at a warm-up simulation. Now your positive tabs are aluminum, typically. So I'm going to set aluminum to the positive tabs. Your negative tabs, however, are copper. Then you have your bus bars. For this particular case, the bus bars were copper as well. You can also have nickel bus bars, and you can abruptly enable a nickel solid in species.n. Your coolant fins are going to be aluminum. And my in and out are again going to be ethylene glycol water composite. And the same for this particular case. Right? And again, I'm going to sort of give it a good initial condition. Since my outflow boundary condition was 1 bar, I'm going to give that accordingly. And inlet, let's say it's about 16000, 1.6 bar. Right? Hit validate, hit OK. Now, given that we have multiple fluid regions connected with each other, we do have to specify events. There's nothing controlling the flow between those different regions, so we don't need cyclic or sequential events. We can just go ahead and set permanent events. If you have different regions connected with each other, fluid regions connected with each other, you are required to specify an event. So I'm going to select my in and my coolant tube, which is permanently open, and my out and my coolant tube, again, which is permanently open. Now, coolant in pipe and coolant out pipe are not directly connected to each other in our geometry. so you don't have to specify any event between these two fluid regions. All right. Lastly, we'll discuss how we model energy or heat release within the batteries. Under the source and sink modeling panel, you could always add an energy source, and you can provide an energy value. This value would come from experimental data, so it's not going to be predictive. You're going to rely on experimental heat release values and feed it to your particular case. For this particular case, we want a predictive simulation and incorporate an electrothermal response. We could be more detailed, and we do have a 3D electric potential solver, which includes electrochemical solution. This is a more detailed solver. We could incorporate this, but we want a quick and rapid simulation. So we are going to use a lumped parameter model called the battery equivalent circuit. The battery equivalent circuit is a 0D model that incorporates an electrothermal response. You provide battery properties. You model the battery as an RC electrical circuit, and then provide a current profile for a particular battery, and it will evaluate a voltage response and a heat release rate. The equivalent circuit model is enabled through the source modeling panel. If you go to source, if you select battery, then you can input the settings for your particular battery model. So let's go ahead and set an equivalent circuit model for our 4 batteries. We're going to model the equivalent circuit as a system of 2 RC or resistance capacitance pairs. The initial state of charge is going to be 0.5. Maximum state of charge based on battery properties are 1.5. The battery capacity, again, obtained from your battery supplier, is 24.3 amp hour for this NMC pouch cells. And then you provide an electric current history or a current profile. You can use a constant value, or for this particular case, I'm going to give a cyclic profile. This is going to be a cyclic profile with a period of 2 seconds. And I'm going to give a simple profile for this particular battery. So I'm going to give a 3.5 C charge-discharge cycle for 1 second intervals. Right. Then after a second, it changes from charging to discharging. Goes back to charging. So this is a cyclic charge-discharge profile that I have provided. I can give a profile name, hit accept. And now I need battery-related properties. So I need battery-related data for the open circuit voltage, which varies with state of charge, and the values for capacitance and resistances, which also varies with state of charge and temperature. These values come from closely controlled experiments, calibrated values from closely controlled experiments. So if you have that data available, you can enter it as a tabulated data here. I'm going to import my data. So I'm going to click the import option. I'm going to go to my folder that contains the data, and it has the OCV data as seen here. So for different state of charge, I have open circuit voltage under charge and discharge scenarios. I'm going to hit OK. The battery properties, since I have 2 RC pairs, I need temperature and SOC dependent values for resistances and capacitances for my different RC pairs. So again, I'm going to import a file that contains all these values and then activate it in my source model. I'm not going to model reversible heat. It's not necessary for this particular application. Under temporal settings, I'm going to make this heat source permanent. Under shape, I'm going to select a region source for my region cell 1. And under stream, I'm going to enable it to stream 1, which is my cell stream. I'm also going to rename the source as BC1. Now the same source needs to be applied for all of your 4 batteries. So I'm just going to copy this 4 times. I'm just going to rename BC2, BC3, BC4. The battery properties don't change, it's the same battery. However, I do need to update the source region. So this is cell 2, this is cell 3, this is cell 4, right? Now, heat source has been enabled in my battery regions, but current is also flowing through my electrical connections like the terminals or the tabs, positive, negative, and also the bus bars. The equivalent circuit model does not work for those particular regions. It's only applicable for batteries. For the electrical connections, I can just create a simple energy source, and based on the current, I can calculate what the heat release rate is going to be based on the current flowing through those materials and their electrical resistivity. So the first source I'm going to set is I'm going to set a source for my positive tab. I've evaluated that source to be 2.283 watts. This is again going to be permanent, and it's going to be in my positive tab region. And this is stream 2, which is the stream for my electrical connections. I'm going to copy this 3 times. I need another source for my negative tab. Negative tab is a different material, so it's going to have different resistivity. It's going to have different heat release for the same current. So I've evaluated that to be 1.483. And for the shape, I'm going to change it as the negative tab region. And the last heat source, predetermined heat source, is going to be one for the bus bar. Again, bus bar has different material, different resistivity, different area of cross section, etc., and evaluated that value to be 5.7 watts. Change the shape to your bus bar, and we're good to go. Lastly, the battery is made up of a laminated layer of cathode, anode, separator material, all stacked on top of each other. So the battery thermal properties are going to be different in different directions. It's going to have a different conductivity in plane, and it's going to have a different conductivity across the plane, so through those laminated layers. In order to enable that, we make use of anisotropic conductivity. So for each battery, say battery 1, I'm going to have, because it's a pouch cell, I'm going to make a selection of orthogonal definition. This is only for thermal conductivity. Now these multipliers work on the solid.dat value that you have specified. So here, the solid.dat value I've specified is 30 watts per meter Kelvin. This is the correct value for the in-plane conductivity. So for the in-plane directions, I can have the multipliers as 1, but for my cross-plane directions, I need the conductivity value to be 0.735, and that multiplier or that ratio comes up to be 0.04245. And then I set my vector, which is x direction, which is cross plane, as you can see here. The other direction can be y, and the third direction is automatically calculated. So I'll do that for all batteries. Also, when I set it for battery 1, I'm going to assign it to the cell region 1. So under shape, I can give a region shape and select cell 1. That's about it. Same thing for battery 2. It's going to be for my cell 2 region. It's going to have the same multiplier and the same directions. Property region selection. for region 4 and cell region 3, right? So anisotropic thermal conductivity has been applied or activated for all of those three different cell regions. Now we can be sure that the correct thermal properties or thermal behavior will be evaluated in our simulation. Lastly, Converge's autonomous meshing capabilities are well suited for these complex battery pack geometries. While the mesh is constructed during runtime by our solver, you still have a good amount of control on how that mesh will be created. So firstly, we set the largest cell sizes in our simulation through the base grid panel. Now, for most Converge simulations, if you are experienced Converge users, you might have been using isotropic grid sizes, where dx equals dy equals dz. But given the nature of this geometry, as you can clearly see that the dimensions in the YZ plane are much larger than the dimensions in the Z plane, or in the X plane, or along the thickness of the battery, especially with these thin coolant fins. So we are going to give anisotropic base grid settings. So 4 mm is good in the Y and Z directions, but in the X direction, I'm going to go finer and have it 1 mm. You can get a good visualization on what that grid size is going to be, and it looks sufficient for, the base grid looks sufficient for the batteries. The coolant fins and some of the tabs and maybe the coolant channels will require some refinement. That refinement is enabled through fixed embedding. So let's look at the different regions that might require refinement. So firstly, we have panel here. We have the thin bus bar regions. So I'm going to give region embedding for the bus bar regions. Regions, bus bar, permanent. I'm going to give a level of 3 because, as you can clearly see, it has thin volumes. Next, I'm going to go ahead and do similar region embedding for my tabs. I have my positive tabs. They're thicker than the bus bar, especially at the base. So I'm going to give a slightly lower embed scale of scale 2. Let's copy this and give this to the negative tab as well. Now, for the coolant pipes that you can see here for the fluid volumes, I'm going to give, again, let me copy this, a region embedding for the coolant in and out pipes with a slightly lower embed scale. All right. And lastly, we have these tiny coolant channels running within the coolant fins. So again, I can give a region embedding for the coolant channels, but I also want, for appropriate heat transfer solution, embedding not only in the fluid region, but also along the surfaces in the coolant fin or the solid region. So what I'm going to do is I'm actually going to enable boundary-based embedding for the coolant tubes. I'm going to select the interface for the coolant tubes, and since it's an interface, you can give embedding on both the forward and reverse side. For the forward side, which is for the fluid domain, I'm going to give scale 3 and more layers. In the reverse side, which is the solid domain, I don't want to have too high of a cell count, so I'm just going to give 2 layers as seen here. Right. Lastly, let's see if that's an appropriate grid strategy for this particular case. Now the tabs here, although they're thicker at the base, they are thinner towards the top. If I give a region embedding of scale 3, I'm going to get very fine cells in areas where I don't need them. So instead, what I'm going to do, instead of a region-based embedding, I think I'm going to make a box that surrounds the top volumes of those thin tabs. So for that box, let me actually measure the center for a box. Let's do this. Let's go to measure, location, average location. Let's pick a vertex here. And let's pick a vertex on this end. right? That'll be the center of my box. So I'll go to fixed embedding, create a new embedding, uh, call it a box type embedding. It's going to be scale 3. It's going to be permanent. Center of the box is the location that I just measured. And then let's think about what the half length of those boxes are going to be. Let's go a bit lower on the y-axis. Let's say, see if this works. Maybe a bit too big. 7. Yep, this sounds about right. Covers good enough volume in those thin tab regions. It's also some initial volume for that tapered end for the terminals. It's good. Don't have to worry about the x-axis too much, but let's just go ahead and give a simple value as seen here, right? So all cells within this box volume will have a level of refinement 3. So I can correctly resolve those thin tab volumes on the top. And that's about it for our grid settings. Now we can wrap up the case setup by making a good selection of post variables that we want to evaluate for 3D outputs. So most important, of course, is temperature, velocity for the coolant, pressure. You might be interested in pressure drop across the coolant channels. I'm also interested in the source value that the equivalent circuit model evaluates. So I'm going to print out the source value in the 3D files, and that should be good for now. I print out the region ID, and then there's no combustion, turbulence, etc. So I'm going to turn off turbulent outputs. There's nothing to be solved for species, so I'm going to ignore this. For the boundary panel, I'm interested in boundary heat flux. This is a thermal management simulation. I'm interested in boundary temperatures, and I'm also interested in the cell heat transfer coefficient, or the HTCs due to the fluid flow. And that should be good here. Hit validate. And lastly, we're going to select appropriate output settings. I do need to include wall output for each boundary surface. I'm interested in evaluating boundary temperatures, heat flux, heat transfer coefficient, etc. I'm not interested in equivalence ratio or some outputs regarding performance, so I can turn those off. Might be interested in knowing the flow behavior across the main coolant pipes and the inner coolant tubes, so I can enable inter-region flow outputs. And then species, writing time intervals. So I want to write 3D data files, let's say not too frequently, but enough 3D data files. So let's go ahead and write a 3D file every 30 seconds. The .out files or the line plots, however, I want to be more frequent. So let's say every 1 millisecond. Restart file saves our simulation at different checkpoints. Let's write a restart file every 60 seconds. And let's also, to prevent any issues with my HPC failing, I'm going to write a restart file every 6 hours or so. Right. Hit validate. Looks like we have a good case set up here. Let's verify that by clicking final validation. And as you can see, the case setup, Studio has evaluated the case setup to be valid. And now we can export this particular case setup, run the particular case, and study the warm-up behavior of this particular 4-cell pouch battery pack. Thank you.